All right, so in the last video, what I discussed was a pretty gentle setup to some of the more fundamentally important ideas that we'll discuss in the run-up to our introduction to linear regression here in a couple weeks. Um, and some of the conversations we're having are some of the more kind of basic and traditional conversations one has with respect to statistical analysis. That includes the conversation of mean versus median. But it's important for us to understand that sometimes these conversations are more than just about opinions, or more than just about feelings, but rather that these conversations are ultimately about measurement, and they're about the refinement of a particular measurement, what we'll refer to as an estimation, and the conversations that surround the distributions of samples, what we'll call the sampling distribution, uh, become fundamental to our ability to trust uh, our estimates, as it were. So while this may seem like a pretty, beige, so to speak, conversation, it's important to remind ourselves sometimes that some of this stuff is about the basics. And it's important for us to keep that stuff in mind. Well, there's the third measure, kind of what we might refer to as the quick and dirty estimators. These are the statistics that estimate things very quickly, and of course carry with them, their own particular problems. We define mean, what we'll call most often referred to as sample mean. We also, of course, discussed median. The third one, which typically gets discussed quite a bit less in statistical sense, but of course you might remember it from elementary school math, and that's the mode. The mode, depending upon the nature of the data in question, depending upon the question itself, the mode can actually be a fairly decent estimator. And again, when we say estimator, what we mean is if we have an estimation for a variable, we want that estimation to be as close to our expectation of what that variable will be. And there are various aspects of the distribution, the data itself, and certainly the way we calculate it, that can affect our refinement of a particular estimate. The simple estimators, there's some refinement. We'll talk about how we might refine mean in just a moment. Not really a whole lot you can do with median or mode. But again, this is all about trying to get a good estimator for a particular variable. It's very important that we have a way to contemplate the expected value, the expectation of a particular variable. Again, if we pull a random draw from some variable, we observe the value, uh, what is that value likely to be? That ends up being very important to statistical analysis writ large. Ultimately, the estimator that we use as some sort of baseline statistical process. And a lot of what we'll do will use the mean. As I mentioned in my previous video, even if the mean is rendered somewhat useless by some distributional factor of the data, we can actually sometimes um, do things to the data that retain the statistical value, the statistical importance, um, but makes the data normal, and allows us, therefore, to rely on a mean as some sort of baseline estimator. So if we have like a symmetric distribution, as we see here, the mean, the median, the mode all equal each other. If we have a skewed here, what we call positively skewed, then the mean is going to be greater than the median, is going to be greater than the mode. Um, And then if we go to negatively skewed, it's the opposite. The mean is less than the median, is less than the mode. Usually in statistics, which one you rely upon when your data is skewed is going to be the one in the middle. So if like our data is skewed in either direction, we can see that the median is in the middle of the three values. So that's why you see median used so often when data is skewed. For example, in the conversation of incomes, which as we know is almost always heavily positively skewed in this particular direction. And so we use the median as opposed to the mean. Um, and again, formulating an estimator for that expected income. Again, that random draw. If we use the mean, then we're estimating that likely too large, given that most people's incomes are down here towards the bottom. And so the median becomes a better estimator of that expected value of someone's income. Yeah, so again, this is about understanding what the distribution means for the information that some statistic estimator has. How good is the information? How useful is the information? I mean, and you can think about useful here. I mean, it's like useful in the sense of the mean or the median giving us a good understanding of something. But I mean, like if you think about the median income versus the mean income, right? It goes beyond just the simple fact that when data is skewed positively in that direction, that the median becomes a more central measure than the mean or the mode. Um, Now, what's interesting about the mode in that context is that oftentimes, if we're thinking about policy, we want to have an understanding of to what extent is there a certain level of misery in our economic system, and so the mode in an income distribution is perhaps very informative because it is likely to be a very low income, and so combined with the fact that the mode, which is the most occurring value for a given variable, and there would be a lot of individuals at the bottom of the income scale. So the mode perhaps is not something we're going to rely upon computationally, but it still maybe contains useful information. And so there's perhaps a distinction between what is useful kind of in and of itself, and what is useful in the pursuit of some more progressive calculation, or both, certainly. All right. So again, the mean is going to be one that we rely upon a lot. In One thing is, you'll notice that we have multiple ways that we try to quote unquote fix mean. So let me but simply say this: like none of the ways that we may articulate to quote unquote fix the problems of a mean, in this case, for perhaps trimmed mean, where we just take the top and the bottom off because maybe the top and bottom have some extreme values. We take them off because we believe that removing those values makes the mean more representative. Now, in that sense, we're trimming the mean for a particular reason. Now, statistically speaking, there are perhaps good and bad reasons, ethical and unethical reasons we might trim the mean in such a way. And I would say so-called Windsorizing your data um, is a little bit more, um, you know, a fancier way of doing something very similar. So if you ever hear the concept of Windsorizing, um, it's statistically sound in a sense, but it perhaps becomes an easy way for the less principled among us, maybe, to fudge numbers and data and things like that. And we'll look at some examples of that in the future, certainly. Some of them are important. Um, So we can trim the mean, but we probably shouldn't do that very often, frankly, ever. I mean, in fact, if we ever were to, we would certainly almost always want to also retain the data untrimmed so that we can then perform deeper analyses on the results that would come from those two distinct samples. Because you trim a mean by removing values, you've changed the sample. The sample's different, and that's not something to do lightly. We also can weight the mean. This is a fairly popular thing to do in certain circumstances where you know you believe that there are perhaps characteristic differences between individuals, such as men and women. And so, let's say if you were providing statistics on like majors and you wanted to sort of present understanding that men and women perhaps may gravitate, historically speaking, certainly, but may gravitate to distinct majors, may be something to consider when presenting analysis using data pulled from those particular samples. So one of the things we can do is that we can weight our means, the so-called weighted mean. Now, what's interesting about the weighted mean is that this comes up a little bit later when we are talking about linear regression, and we do a weighting that is sort of similar to weighted means, and it's just a way to correct for, um, let's say, sort of latent influence in somewhere in the data. There's some influence in the data that you believe masks something important about the statistics that you're presenting, or obfuscates from them, or exacerbates them, whatever. And so you can weight them relative to these proportions, and it can be a way for you to correct a little bit, to kind of remove some of that, albeit granular, but still statistically important influence. Uh, because a lot of what we discuss in economic research ends up kind of boiling down to questions of influence. What is the influence of this particular policy on some metric? What is the influence of this particular trade flow on some economic outcome, whatever it is? So whatever those proportions are that you think might be influencing the data, weighting can be one way to do it, and there will be other ways to statistically deal with those sorts of concerns over influence. But this is where you sort of you start to get your first peek into how deep these questions go, statistically speaking. We're thinking in terms of joint distributions of variables that have multiple joint distributions within them, with respect to other variables. And then perhaps most concerning is that variables can be jointly distributed with so-called unobservables, um, and unobservables are exactly what this sounds like they are. They're things that we know exist, but we don't have records of them. They're not, data is not collected on them. And we'll talk a lot about observables later in the class. So sometimes people try to use sort of weights and again, recalculating the mean in such a way to kind of so-called fix it. But whether or not you're fixing the right thing, or by trying to fix it, you're actually making it worse. Again, the weighted mean is something that you want to tread very lightly with. It can be useful, but it's again, you don't want to over rely on it. It becomes another potential way of doing something, but no more, no less. The geometric mean, this is just simply the mathematical recognition that certain data, usually we use geometric mean because we're dealing with things that have like a multiplicative process, like compound interest, or economic growth. We know that these data, sort of the outcomes of these data, the data generating process produces a variable that has a multiplicative process, or a geometric growth. And so in order to measure that, we have to apply different um, methodologies, so to speak. We have to think about it differently, right? The difference between arithmetic mean versus geometric mean is that in an arithmetic mean, we're sort of allowing for data to kind of only grow linearly. Otherwise, there's a real failure of the traditional means and so on and so forth. Whereas if we try to accommodate the fact that there are certain data that have nonlinear attributes, then that would be an important way for us to deal with the statistical problems that would stem from that. Again, this is going to be a topic that we deal with considerably when we get to regression analysis. Regressions in which there are potentially nonlinear relationships amongst the data, amongst the variables rather being used to be accommodated for in statistical ways. So, in a way similar to that, the geometric mean is simply a way for us to accommodate the fact that data sometimes are generated in a nonlinear fashion, in a geometric fashion. Again, it's not something that we'll come across very much. The way that we deal with nonlinearities later on is, it's a little bit more straightforward than that, but it's there. It's again, it's something for us to kind of keep in mind and have access to, and it shows up here or there. It shows up in some time series analysis and things like that, which we'll get to when we talk about forecasting. All right. So why are we all here? What's all of this conversation? Well, we're building to how important it is for us to consider the dispersion of our data. And when we think about dispersion, the extent to which our data is spread out, usually people will point to the variance and standard deviation as those particular measures. They're the most common measures of dispersion. They're the sort of simplest for us to kind of wrap our head around. Um, but the thing about the variance and standard deviation is that very similar to the base measures of mean and medians and these things are going to be affected by and rendered inefficient, shall we say, potentially, with respect to the underlying distributions of the data being used. So variance and standard deviation perform best when the data is nicely normally distributed. And the less it is those things, the more we have to think about either how we're using variance and standard deviation, or potentially even looking elsewhere to other means, no pun intended, of performing calculations. So dispersion, I think, is easily considered in the context of the what we call the deviation. The deviation of a variable is simply the extent to which an observation is away from its mean. So in this data here, you see in front of you, the mean is 4. You have 4 data points, one at -2, one at 1, one at -1, one at +2. And you can see that it's very easy to calculate the deviations. So when we say deviation here, we mean deviation from the mean. Now it's important because this is the beginning of a lot of the statistics that we will come across in the near future. And it begins right here with this notion of a deviation, which is very simple. All right. You have data that is, distributed in some way, has value in some way. The blue dots are the actual data. And it's interesting in many ways. This picture kind of promotes the idea that the mean is a calculation, whereas the data are the data. And there's a difference between those two things. And that is part of the reason why distributions and how they affect the calculation of the mean and things like that. That's why they matter, right? Distributions affect the deviations, right? So think about that. The extent to which your data is distributed affects the deviations because it's the dispersion of the data that in a way ultimately defines how the data will be dispersed, or sorry, will be deviating from some central measure, most likely a mean. But again, you could use median or something else, but most likely a mean. In this case, in this picture, we're using a mean. All right. So variance and standard deviation. Um, very simple calculations. Again, remember what I say, keep this in mind. Statistics, everything is a fraction. There's a numerator, there's a denominator. Know what's in the numerator, know what's in the denominator. Now, it's important to point out here that this is the population variance. There's a distinction between the population variance and the sample variance, which we'll certainly get to and discuss. Obviously, the key connection here between variance and standard deviation is simply the square root of the variance. But let's look at what the variance is. So I'm highlighting this particular part of the equation, this xk minus mu. In our context here, mu is the mean of x, it's the population mean of x, and xk is simply an observation within a sample of x. So you'll notice here that we're taking the observation value, we're subtracting its mean. What does that sound like? That sounds like a deviation. All right, so this is just deviations squared. So you take every observation in your data, you subtract off the mean, and you square it, and that gives you the numerator. Again, very basic concept here. And then you just divide it by the sample size. You divide it by n, and that gives you variance. This is how we denote variance. Sigma squared, lowercase sigma squared to be exact. And then sigma is the way we denote standard deviation, and it's the square root of variance. Now, what do of course, do these things mean? Well, again, should go without too much kind of analysis that, again, variance and standard deviation become ways that we think about the level of dispersion of the data. And it becomes, again, important information about the data themselves, and then important information about the statistics that we would, need to compute from those particular data. So, again, I'm bringing back my stata here. We're going to go back to this sort of, I don't know if you really want to call it a Monte Carlo simulation. I'm just using the random number generating ability of stata to, generate, made up data for me, which then becomes really nice way for us to look at the effect of things like sample size, the effect of things like skewness on various measures of, again, those important considerations like variance and standard deviation. So let's just look at the x variable, which we had created before, which has a mean of 10 and a standard deviation of 2.5. So we know what the mean is, what the 2.5 is, because we told it what it was. Now, it's important to realize that, as you'll recall, this is the population values. So we're saying that x is a variable that is population is distributed normally with a mean value of 10 and a standard deviation of 2.5. When we actually generate the values to create the sample of x, what we'll find out is that it's very close to those values, but not quite, because it's a sample drawn from a population. And that's the nice thing about the sort of Monte Carlo setup, is that it allows us to sort of mimic the sampling from some sort of population distribution. So we get an idea of the relationship between what we call the sampling distribution and what we call the population distribution. So this is just, we're going to do a histogram of x with a mean of 10 and a standard deviation of 2.5. And we got this is 10,000 data points. Now let's just kind of move on to, again, where this is important for us. And where this is important for us is the extent to which we can measure the dispersion and understand the nature of the distribution, so that later on, when we rely upon things like linear regression, we can feel good about them. Okay, so x here is a random variable with mean of 10, standard deviation of 2.5. We could, sort of already, estimate the measure of variance, because we know that variance is just standard deviation squared. So we can, variance in the context of like this particular example is a little weird, because we're already kind of, we can put it together without actually doing any calculations, but we can let the randomness generator of stata produce a sample and allows us to kind of look at things. So if we summarize X here, if we just summarize and then X, what we get is some basic information about X. We get the mean, which you see here within the sample is 10.01. The population mean is 10. Sample mean here is 10.01 or 10.02 if we round up. Excuse me. Standard deviation is 2.49. Again, 2.49 or 2.48. If we round up, it's 2.5. So again, not quite, but very close. And then we have the min and the max, right? Again, we have the mean and the standard deviation. This is some good information, but we always want a little bit more information than that. So then we jump to the second way we can write this. We can do summarize X detail. We hit that, and then we get this. And this, what it does, is gives us a lot more information about X. We have the mean, standard deviation, which we already had before, but then we get the variance. We get the skewness. We see it's very, very just it's a little bit of negative skew, but that's not really much at all. Again, very little kurtosis as well. Yeah, we get some nice percentiles as well. So detail here, this can be a nice way to just quickly know about your data. You're going to find yourself doing this. Students in the past whose work was really good were the ones who really bought onto the idea that you want to know what's going on with all of the variables in your data set. Even, data sets that are huge, you don't need to know what's going on with every single observation of a data set, but you need to know the mean and the variance and standard deviation and the nature of the distribution. That's stuff that you have to know. Okay. So there's variance and there's standard deviation, again, just a measure of the skewness, or I'm sorry, measure of the dispersion. If we, for example, were to alter X instead to be, have a much higher standard deviation, we're going to leave everything else the same. I'm just going to run all of this code right up until this. So it'll do that, and it'll do the histogram of X again. So we'll do that. Oh, actually, what I need to do here is I need to add to the top of my code clear all. If I do that, then I can just loop my code over and over. It becomes very useful to do that. I think, by the way, I'll probably say this a lot, but I think that one of the best ways that you can learn, not just how to do things in Stata, and then, obviously we're also going to look at things in R, but also just learning statistics. This is a great way to do it, just to kind of mess around with, something like a Monte Carlo simulator, is a great way to kind of learn, the basics. And that was something that I did after graduate school when I started teaching this stuff, and I had to understand it well enough to teach it. I spent a lot of time just on Stata, just messing around, kind of reminding myself of the basics. Okay, so as you can see here, we've kicked up the standard deviation of X compared to what it was before. You really can't tell visually much of a difference. Although if you were to go back, you would see that the data is more spread out. It goes in larger directions. In fact, if we just do the summarize of X here, we'll see that in the min and the max. So you can see here the min here is -10, the max is 29. So this is the randomly distributed X with a standard deviation of 5 instead of 2.5. So -10 and 29. If we go up to the one of X where it was only standard deviation of 2.5, we can see that the min and the max are much smaller, -0.2 and 19. So there you can see just in the numbers, those two numbers, the physical difference between these data. These second data with larger standard deviation are just much more spread out, and in a very predictable way. So that's good for us. When data are normally distributed, whether or not the standard deviations are large, or therefore the subsequent variances are large, so on and so forth, that stuff's not a problem. In fact, oftentimes the larger the variances, the better when it comes to actually statistical analysis, because it's going to be in those variances where we actually are able to measure things. If things don't change much, their variance isn't much, and there's not a whole lot of information that you can glean oftentimes from data that doesn't vary much. We want high variances oftentimes, and so, but we want high variances normally distributed. So you can see we retain the shape of the normal distribution completely, but we have a much higher standard deviation. So statistically speaking, it's still nice and sort of well behaved. I guess is probably a good way of putting it. Okay. So let's go back to these slides now. All right. So again, variance standard deviation. Um, you know, basic measurements and statistics, something that I'm sure you've come across probably multiple times, but it's important to put it into particular context. It's important to see it also in the stative example, so you can actually very quickly draw what variance standard deviation is. Now, what we actually were seeing in that particular example are these measures, which is, or I'm sorry, this measure, which is sample variance. Sample variance is almost identical to the population variance, except of course you'll notice in this equation we have X bar. This is just sample mean as opposed to population mean. So mu is population mean, X bar is sample mean. Again, observations of X minus the sample mean, squared deviation, just like before. But the difference you'll notice here is instead of subtracting off n, we're subtracting off n minus 1. The reason why we're doing this is because, and we'll talk more about degrees of freedom when we get to sampling and hypothesis testing later on this week. But basically, the reason why we subtract off 1 there instead of n, it's n minus 1, has to do with degrees of freedom. Basically, by doing that, what we acknowledge is that we've calculated a mean using this sample, because it's not the population, right? In the population, there's sort of like theoretical, like, whatever n is, it's sufficiently large, right? In samples, we're obviously concerned about sample size. And so we're concerned about what's going on in that denominator. And so n minus 1 is a way for us to sort of recognize that the calculation of the mean says something about the statistics that we're going to be able to compute. So we go n minus 1 here because we lose a degree of freedom. Basically, that comes down to the fact that we lose some randomness because mean is non-random here. But we'll talk a little bit more about that when we get to sampling. So, the basic empirical rule of the standard normal distribution is, best illustrated by the 68, 95, 99.7 rule, or what we always just called 68, 95, 99. And this just gives us a rough idea of, with respect to the dispersion of our data, where do we expect to see values? Again, you're going to kind of see that language come up a lot. Expect. Where do we expect? There's a reason why we care about that. Where we expect data to be and where they are, that's kind of the crux of the whole deal. And our willingness to acknowledge that language, that notion of expectation of, is important. It draws from probability theory, it draws from statistical theory, and so it makes our modern statistical analysis, foundationally true, not just kind of cosmetically true in a modern sense. So again, standard normal distribution, population mean, or we can just call that a mean right now, of mu. And then you'll see on either side of the distribution here, we have the mean plus standard deviation. Again, I'm sure you've seen this before. And then, as we increase standard deviations, we see that the area underneath the distribution declines, reflecting the fact that we expect far fewer observations to fall over here than, of course, we expect observations to fall over here. And again, we think about this in the context of probability. So you're seeing already the mixing of probability theory and statistical theory here. So we're bringing in the idea of expectation, we're bringing in the idea of the probability distribution function, and then we're also bringing in the statistical reality of things like variances and standard deviations and whatnot. Now, the reason why we refer to this as an empirical rule is because later on we will make decisions statistically based upon where values fall along this particular continuum, whether they fall within the 68% of data we expect to be within 1 or -1 standard deviation of our sample mean or population mean, as it may be, or is it going to be within two or -2 standard deviations, which is 95% of the data. Um, Later on, when we do hypothesis testing and we're measuring effects of variables and other variables, it will be where those measured effects fall relative to some assumed standard normal distribution that will allow us to either reject or fail to reject our hypotheses that we're testing. So that's why we refer to this as the empirical rule. So if we go back to this data here, again, one of the things we can do is we can throw in bars that reflect the mean and standard deviations of our data. So let's go back to 2.5 because that's when I originally made it. And then we're just going to rerun this. And this time I'm going to go all the way down to this hist. Here what I've done is I've added vertical lines along the mean, 1 standard deviation above and below, 2 standard deviations above and below. So it'll give us lines for that 68%, 95%, so on and so forth. And then what we can see is we can see how problematic that is when the data is not normally distributed. Okay, so let's bring up this data here. Bring up our do file. And again, like I said, I'll always post the do file. Will get posted to classes along with the video. And I'll try to post the do file I'll try to remember to post it to YouTube as well. That way, if anybody who's not taking my class right now happens to come across this lecture and whatever you want the notes, you'll have that as well. All right, so let's just run all this. Again, we've changed the X variable back to having a standard deviation of 2.5, changed nothing else. Let's see, oh, this is gonna be fun. I love watching the histograms get made. Maybe love is a strong word. Okay, so here we have this middle line. This is the mean of X, which is 10. Again, population mean is 10. And then 1 standard deviation over, which standard deviation is 2.5, so 12.5, and then 7.5. So again, the idea is that 68% of the data is going to fall between 7.5 and 12.5. That's, and then 95% of the data is going to fall between 5 and 15. And we can actually take slices of these, which is, not perhaps terribly useful for us, but it's just interesting that you can actually slice off these things in terms of probability. So, like for example, if we like all the area underneath the curve there, like that's obviously 100% probability. And then if we just chop off this tail here, so we know that between these two we expect 95%. So then that means like this is 2.5%, this is 2.5%. So we can actually like you have a 2.5% probability of a value being found in this particular tail. Now, what's interesting about that is that when we get to like business forecasting and things later in the semester, we'll learn that a lot of people make a lot of money because they bet on events happening in these things, in the tails, over here in the tails. And there's this concept called like fat tail risk that we'll talk about, which is really interesting. So, a lot of people think that all the glory is here and the means and everything within 1 standard deviation because that's where everything's happened. But these events over here, despite the fact that they're low probability, they happen. And if you can time it well, or if you're smart enough to figure out when those events happen, you can make a lot of money. So-called black swan events, I think, is what they're referred to. I remember I read that book by Nassim Taleb called Black Swan. It was a pretty interesting book.